Good afternoon, class. In today's video, what I wanted to do is to finish the series on optics by talking about the thin lens equation. So this time, we're going to actually focus on the math portion of how to deal with all of those ray diagrams, as well as all those different lenses. So for this one, what we're going to do is we're going to, first I'm going to write it out just with words and then put a little bit of a formulation in there just so that you'll understand the variables, mostly because these variables I know are not usually the kind of variables that you would see in a normal equation, so I just wanted to make sure that those were clear. So the thin lens equation says that 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. Or in the way that I would normally tend to write it out, or it is traditionally written out, is 1 over O plus 1 over I equals 1 over F. I know that O looks like a 0, but that's an O. Trust me, that I know it doesn't. My O's and my zeros may look kind of the same, so please bear with me on that one. Also, since we're here in the thin lens equation, I decided to talk about magnification. So the magnification of an object is going to be equal to, or given by capital M, is going to be equal to the negative of the image distance over the object distance. So if you know I and O, you know what the magnification of the object is. So given that, what I wanted to do was to go over about 3 examples of what happens with differing focal lengths, with different object distances, how that affects the image distance, and what the magnification of it will be. And hopefully you'll see why we set up the rules the way we did. So with this equation, what we have in our first one, I'm starting off very general. I'm trying to make this as simple as I can, mostly because I just want to show the physics and not necessarily any of the math that goes behind it, because the math is not really the feature. The physics and the physical features of the lenses and this equation are what's important. So my focal length is 1 meter. My object distance is going to be 1 meter. So if you have something at the focal length if your object is at the focal length of the lens, what's going to happen? What image will you see? Hopefully you remember from my last video when I actually brought the lens closer to the camera, what happened to the tree in that image. Before it flipped, right? It started off inverted, and then it all of a sudden went out of focus, and it seemed to flip around. So there was that length where all of a sudden you couldn't see the image no matter what I did. And that's actually important, because what you find from that is that as you do the math, you get 1 over image distance is 0, which means that if you flip that over, that's approximately infinity. That would be your image distance, which means you can't actually see an image. Like, there's no image to see at all. In fact, the magnification would be infinite. So, which is also has no meaning, in terms of mathematics, and in terms of physics. What does that actually mean? What would you actually see? It means that there would be no image, not even an inverted image, not even a blank screen or something opaque. It's just no image can be discerned from at that point. That's what this example is trying to show, and hopefully you saw the answer to that in real life in the last video that I did. So that's example number 1. What about if your image distance or if your object distance is within the focal length of the lens? What would that look like? So then you would want to know what the image distance is. So again, my focal length is 1 meter. My object distance is half a meter. So what would be my image distance? Well, when I figure this out, I plug it in and I do my math. I find that my image distance will be negative 1/2 meters. Wait, that's behind the screen. That's going in the opposite direction of where it's supposed to go. So light is supposed to travel from left to right. So that means the image distance, which is supposed to be to the right of the lens, is now going to be on the left of the lens. And of course, we've seen that from concave lenses, even from the example I showed you in the last video when I moved it closer and that tree went upright. It'll be a virtual image. The image distance will be negative. That means it's virtual, and therefore it is upright. And we actually can see that. In fact, what we see is that the magnification, when we plug it into the magnification equation, it is instead of it being negative or something like that, it is +1. So it is virtual, upright, and unmagnified. That's basically what we're saying. Now, of course, that's the second example. What's the third example? The third example is same focal length, so basically it's the same lens, but this time the object distance is now 2 meters. It's twice as far as far away as the focal length. So what will the image be? Well, here we go. When we plug in all our numbers, we get that the image distance will be 2 meters. So it'll be actually the same. It'll be the same distance as the object will be. So if it was, let's say this was our center, and our object was over here, then our image will be about over here, the same distance away. And what will be its magnification? All right, let's plug that in. This is a positive number, so we've got magnification is negative image distance, which is +2, over the object distance, which is just +2. So negative positive over positive is still going to be a negative. So it's going to be -1. And so that means the image is going to be flipped, so be inverted, but it will be magnified by the same amount. So if it's 2 meters tall, and if the object was maybe say 2 meters tall, the image will look 2 meters tall, just inverted. And you actually got to see that with the when I had the lens maybe about back here. You saw that the tree was actually upside down, but about the same height. Now, of course, if I change these numbers, this magnification will change. And all of these things. Anytime I change those numbers. And so that's why you'll have the practice of doing that. Hopefully those practice problems will give you some idea of what happens when you start really adjusting optical instruments, and when you move these lenses around. They'll give you some examples of how to get a feel for what kind of image you will see, whether it be real, whether it be virtual, whether it will be upright or inverted. And how all of that will look. Hopefully it'll build your intuition a little bit, because that's always the goal of physics. So that concludes this example video on, at least this more mathematically technical video on optics. Good luck in your studies, and may the force be with you.